Okay, so I do want to start with let's start with an introduction. Professor Wada is here hanging out with us today. So he's here to evaluate me. So yeah, just so you know why he's hanging out. Uh, and then the next thing I want to talk about kind of in housekeeping kind of stuff is this is the first time we've met since our test last week. And so I'm kind of springing this question on you guys, but I wanted to see if anyone wanted to provide any feedback about how the test went. So, so either good stuff, bad stuff, things that you could see that would need improvement. It was my first time doing a test that way with cameras on and everyone kind of taking it together. If you think of something after and want to email me or text me about, that's fine too. But does anyone have any feedback for how it went? Well, thank you, Noah. That sounds like a great review of the process.
Oh, yes, I wanted to say a few things, or like not a few, but just say,
Go for it.
yeah, I agree. I really liked it. I felt like when I was doing it, I understood everything that was going on, even if I didn't 100% know it. I know we had gone over it, and I liked that it was really straightforward. And just comparing it to last semester with you, I really appreciated this test, like this format of the testing. I thought it was way more helpful for us.
That's good. Yeah, last semester when we did a lot of multiple choice style, those questions came from like the test bank that comes with the book. And this one I wrote myself. So it makes sense that it would fit more with what you guys have learned because I'm, matching it to how I teach as well. What about the camera thing? So I don't know if any of you guys have used Proctorio or Respondus or any of those, but having the cameras on, that was all okay. We all did fine.
Yeah, I kind of got because last semester in the spring I had to do the same thing in another class, so I'm generally used to being watched.
Good. Okay, so if you guys think of anything, I appreciate the positive feedback, but if you have anything negative or more anything else you want to share, you can always text me or email me, but it's good to hear the feedback. Um, let's see, what else was in my little notes here? The experiment that we're going to talk about during lab today, I got a couple texts saying that one of the pictures wasn't showing up, so I did re-upload that. If you're not seeing it still, just let me know. I can still see it on my end, so I can't always tell if it's been fixed. And then Nate, our SI leader, and Brandon, the SI leader from the morning class, are combining forces so that you guys can attend both sessions and get extra help and extra tutoring. But they're trying to make sure that the schedule fits with everybody. So I did post a link in the announcements on Canvas. So please help them out. Click on the link, take a couple minutes to fill out the survey so that they can get the times right, so that they're times that you guys can actually attend. Okay. Oh, one more thing. I'll say it now just since I brought it up. We have been using Beyond Labs. There's a new version of it that's out that's web-based, so you don't have to download it. So I'll post some information about that probably tomorrow. But it might help you guys out, especially if you want to switch between devices. If you want to, do it on a tablet or something. So I'll post the info for that. It's their newest version, which I think will be very beneficial, especially to future classes, but you guys will probably benefit from it as well. Okay. We are going to start chapter 19 today. Let me get my screen all set up here. Our next little grouping of chapters is 19 and 20, and they go really well together. So 19 is aldehydes and ketones, and chapter 20 is carboxylic acids and their derivatives, which is kind of just a catch-all way to say all the other carbonyl compounds. So these all have very similar reactivities, and you're going to see a lot of those same mechanism steps, those patterns repeated, which is really useful because that helps us learn not just what's happening, but why it's happening. So new functional groups, new chapter. We got to start with the basics. So reminder on some of this stuff, well, probably most of this stuff, but a carbonyl group is when we just have a carbon double bonded to an oxygen. And then what's attached to that carbon is going to determine what functional group it falls into. So we are focused in this chapter on ketones and aldehydes. So a ketone is when we have two carbon groups attached. And I'm even going to put the little tick mark next to one of them. What does it mean when we put the tick mark next to one and not the other? Have we talked about this? Yes, perfect. I see in the chat. Yeah, so they're different R groups. So it just means it doesn't have to be symmetrical. It definitely could be, but it can be asymmetrical. And then the aldehyde, an R group on one side, and the hydrogen on the other. The couple examples on the bottom there are showing us some naturally occurring aldehydes and ketones. Notice that they all are different flavors. So a lot of carbonyls have strong scents, so sometimes good, sometimes bad, but they're usually fairly aromatic in their smells. Benzaldehyde is one of my personal favorites, which is probably a very nerdy thing to say that I have a favorite chemical, but it's true. It also, my organic chemistry professor's cat was named benzaldehyde, so one of those weird ones that's always stuck in my head. Gotta do some nomenclature. So new functional groups, new nomenclature rules, kind of. We're sticking to the same rules we know. We're finding the longest chain that contains a functional group. We're giving it the lowest numbers possible. We're putting substituents in alphabetical order. All of that stays the same. We haven't changed any of that. Because we're dealing with functional groups, we're changing the parent chain name. So for an aldehyde, we're going to end the name in AL, or aldehyde. For ketones, we're going to end the name in -one, so for ketone. So we have a couple examples on here for both of them. For aldehyde with methanal, ethanal. If you're saying these out loud, you have to be really careful with pronouncing them so it doesn't sound like methanol. So the alcohol versus the aldehyde, the way they sounds very similar. And then of course spelling them is literally one letter different. So be super careful with that. Ketone examples, we have a 3-hexanone here. So we're saying which carbon the ketone is on. 6-methyl-2-heptanone. So notice that the ketone gets priority because it's our functional group. So we number from right to left in that example. Why don't any of the aldehydes have a number for where the aldehyde is located?
Terminal.
It's terminal, yeah. It has to have that hydrogen on the end, so it's always going to be on carbon number 1. It's kind of the same thing with this propanone over here. There we go. It's a 3-carbon chain, so if it contains a ketone, it has to be on that second carbon. If it was on the first carbon, it would be an aldehyde instead. So just a couple kind of reminders or ways to think about it. All right, let's practice a couple. So let's see. Let's start at the top. I need to get my little zoom controls out of the way here. So our first one there, we have an aldehyde, we have some substituents, we have an alcohol group. I'm starting with this one because it has the most new stuff for us. It does have our new functional group. It has an aldehyde, but it also has an alcohol. So it actually has 2 functional groups in it. So I'm going to go to our next slide here for a second. This is straight out of your book. This is Appendix 3. This is telling us what to do if there's more than one functional group on our structure. The functional group list over here is in priority order. So that means that whoever is highest on that list gets to be part of the suffix or part of the parent chain name. And then that list there in the middle is giving us a little rundown of what suffix we would use. So if we have more than one functional group, whatever is below the higher priority one, we name it as a substituent. So we have an aldehyde on our example problem, and we have an alcohol. So for the alcohol, we're going to name it as a substituent using hydroxy. This is really going to come into play in the next chapter, because in the next chapter, we're going to learn how to name all of those. Everything else we already know how to name. So we're going to learn how to name the top half of that chart next semester. I said next semester, didn't I? Next chapter. All right, so let's go back to this example then. Where should I start numbering this thing?
On the aldehyde?
Thank you. So 1, 2, 3, 4, and then am I going to go up to that ethyl group or over to the alcohol?
To the alcohol.
We are going to go to the alcohol. And the reason for it is a tiebreaker that we haven't talked about probably in a while. Because if we went up towards that ethyl, it would still be a 6-carbon chain. So our tiebreaker, if we have 2 chains that are the same length, is we look for the chain that has the largest number of substituents. So if we went 5 and then 6, the only substituent we would have would be that 2-carbon chain with the alcohol attached. But instead, if we number it the way that we have, we would have the alcohol and the ethyl. So 2 substituents wins out. Okay, let's see. We have a hydroxy. We have these 2 carbon groups. What are we going to list first? What comes first alphabetically? Good, the ethyl. I see it in our chat there. So we're going to say 4 ethyl. And what's going to come after our 4 ethyl? Oh, I don't know who. Justin, was that you that just tried to talk? Because you sounded like a really fast robot. So it's not going to be the methyl.
The hydroxy group?
The hydroxy, our new one. So 6-hydroxy. And then we'll add on that methyl. So where's our methyl? Number 3. Oh, and then we actually don't need a dash because we don't have a number. So it is hexane. So we're going to call this hexanal. Questions about that first one? Okay, not too bad, right? All right, what about our next one? So well, there's kind of double functional groups. We'll talk about that alkene though. He kind of breaks the rule. Where should we start numbering this? On the left by the bromine or on the right? Oh, could you be extra specific? Yes, you could call this hexan 1-all or 1-hexanol. That would work. It's being a little redundant because the aldehyde has to be on carbon 1, but it's not wrong. It just gives you extra info. So where should we start numbering this one? Should I go here or should I go over there? So by the ketone or by the bromine? Good. So we got a few votes in there, but the majority does win there. So we're going to start over by the ketone. So 1, 2, 3, 4, 5, 6, 7, 8. We're starting by the ketone because the ketones are functional group. So even if the bromine is closer to to the 1, it would give the bromine the lower number. We want the functional group to have the lowest number possible. So bromines are only substituents, so we can start with that. So 7-bromo. And then our parent is oct, so octane, octene. We got a few things we got to name in here, though. Actually, I'm going to erase this and move it down a little bit so I have room for everybody. So the parent chain would be octane, but we got to change a few things in that. What do you think we're going to call this? So it can't be octane because we got to say everything else that's included. Go ahead and type it in the chat. Make a guess. That is perfect, Nell. It is octenone. And I'm going to leave a little space here for some numbers. Yeah, the oct is for the 8 carbons. The ene is because we have an alkene. The one is because we have a ketone. And then I left a space for 2 numbers. What number should I put in the first space, the one that comes first? Good, Justin. It would be 4,3. Get rid of my arrows there. So we put the 4 first because it goes with the ene, and then the 3 second because it goes with the one. So we're listing them in the same order as they are in the name. There's a couple different ways to do this, though. We could also write it as 4-octene 3-one. So same idea, we're just inserting that 3 in the middle. Or we could write it as oct 4-ene 3-one. This one is probably the most common way to see it, where it's broken up a little bit. But in my experience of teaching this class many, many times, I find that students like this one the best when they are writing out their own answers on a test, because it doesn't leave a whole lot of room for error. You have all of those pieces kind of put together. The 4 goes with the ene, the 3 goes with the one. It seems to make a little bit more sense when you're kind of writing it out. We're missing something for this name, though. What are we missing? Something we haven't talked about in a while.
Trans.
We are missing stereochemistry, but it's not trans. Cis. Yeah, cis or Z. Actually, both of them would work in this scenario. So I'm going to put cis here. And the reason why cis works is because the hydrogen on carbon 5 and the hydrogen on carbon 4 are on the same side. So that's why we can use cis. We could also use Z. And the reason why we could use Z is because the high priorities, so that would be the ketone and the rest of the chain, are on the same side as well. So that's why we could use Z in this scenario. But it does have some stereochemistry in there. Okay, what about the last one? Moving my zoom functions out of the way again. Where should we start numbering this one? Left or right? Yeah, I agree. Let's start on the left. So no matter which way we start, our ketone will be on carbon 4. It's right in the middle of that chain. So we want to start numbering it so that our substituents are at the lowest positions. We have some more stereochemistry with this one. So I'll leave a little spot here. I'm going to put 2 and then a space and 5 and a space. So we'll put some R's and S's in there as needed. But we'll start with the chloro. So it comes first alphabetically. So 2 chloro, 5 methyl, and then what are we going to put for our parent chain?
heptanone.
Good, heptanone. And we do need a 4 in there to say where that ketone is at, but 4-heptanone. And you could break that one up like the other ones too, so you could call it heptan 4-one as well. Okay, what about our stereochemistry here? So carbon number 2, chlorine's the highest priority on there. Then the rest of the chain, then that methyl. So we're doing 1, 2, 3. We're going to the right. So is carbon number 2, is it R because it's going to the right? It is an S. So our lowest priority is in the back, is pointing towards us. It's a wedge, and the highest priority is a dash. So that's when we do the opposites. And then I'm going to fill in this R that Justin says it is, and then we're going to count it out. So for carbon number 5, the ketone part, the kind of the larger side of the structure would be highest priority, and then the ethyl, and then the methyl. So 1, 2, 3. So we're going to the right, and our lowest priority is on a dash. So it sticks to the right. Questions about any of those names in that little stereochem refresher? Okay. Oh, we did that. A lot of times when we start a functional group and we start talking about reactions, we start by talking about how to make them, and then we talk about how to react them. We've already talked about how to make aldehydes and ketones quite a bit. So these numbers on the slide are the chapters and section numbers of where we saw these reactions before. So we have talked about how to oxidize alcohols, how to break apart alkenes and alkynes, and then how to add that acyl group to a benzene ring most recently. So we've done this. It's a nice little review section in the book. We're not going to go over it again though. What we are going to talk about is how to react our ketones and aldehydes. And before we get into the specific reactions, we're going to look at where it's reactive and how it's reactive. And so on the screen here, we have our ketone. And notice right here, it has like R with an H in parentheses. So really, that's just trying to be generic. It's saying that this could be a ketone or an aldehyde. It's just kind of representing either one. The reactions we're looking at are called nucleophilic addition reactions. So not a substitution, not an elimination, but an addition. So we're going to be adding a nucleophile to our carbon. We've seen addition reactions before. The most of the ones we saw before were in our alkene section. So when we did an addition reaction with our alkene, we were adding something to each carbon, and that double bond had to break. So we're doing the same thing here. We're going to add something to our carbon, and we're going to add something to our oxygen, which is just going to be a hydrogen, but we're going to break that pi bond in the process. Here's how our mechanism is, or here's kind of like the driving force for our mechanism. This arrow right here, this is our nucleophilic attack. The carbon in the carbonyl is partially positive. It's bonded to an electronegative atom. And so because of that, we have an attraction between our nucleophile and our carbonyl carbon. And then at the same time that that nucleophilic attack happens, the pi bond is going to become a lone pair on the oxygen. And so it is pushing that reaction forward because of that difference in electronegativity between the oxygen and the carbon. Just that part right there, that oxygen-carbon double bond, that's one of our resonance patterns that we learned way back in chapter 6. So we already know that that partial charge on that carbon and oxygen are pretty strong. When we compare reactivities, we have a ketone all the way to the least reactive side, and then our aldehyde, and then in the most reactive category is formaldehyde. So formaldehyde has a hydrogen on each side. So let's kind of focus on the ketone and talk about why it's in the least reactive position. And there's two reasons. The first is that our carbonyl carbon, is partially positive charged, which really means that it's kind of like a pseudo carbocation. And we already know that carbocations are more stable when they have more things attached to them. So if we have two R groups attached to it, that means it's going to be more stable, and more stable means less reactive. The second reason why ketones are less reactive is sterics. There's just more stuff in the way. It makes it more difficult for the nucleophile to attack. And along that same lines, a ketone that has smaller R groups is going to be more reactive than a ketone that has larger R groups. And that's just based off of sterics. So more stuff in the way just makes it harder for that nucleophile to get in there and react. So we're going to look at the general mechanisms for this. So every reaction we're going to look at in this chapter is going to have these same two basic steps. There might be some additional ones, or we might see these steps repeated, but they're all going to contain these steps. And this is divided into two halves on this slide. The top half is the basic mechanism. So meaning under basic conditions, so negatively charged particles. In that first step, we're doing the nucleophilic attack. So our nucleophile is attacking that carbonyl carbon. The pi bond becomes a lone pair on our oxygen. In the second step, we're doing a proton transfer. So the negatively charged oxygen's grabbing a hydrogen from the water, and it's creating a hydroxide. So the hydroxide can form because we're in basic conditions. And then there's our new product. Our carbonyl carbon, or what was our carbonyl carbon, is now bonded to the new nucleophile and the alcohol. In the bottom half of the slide, same mechanism, but now under acidic conditions. So notice it's the exact same two steps, just in opposite order. So we're starting with the proton transfer, and what we're using is our acid catalyst to do this. So HA is just A for acid, generic acid. Once that oxygen is protonated, it's going to cause the carbonyl carbon to be more reactive. It's going to weaken that pi bond, because now that our oxygen's positively charged, it's going to pull the electrons towards it even stronger. And so that carbonyl carbon has now going to have a stronger partial positive charge because those electrons are getting pulled away from it. So that's why we will often use an acid catalyst to help these reactions along. So the next step then is our nucleophilic attack. So the nucleophile attacks that carbonyl carbon, pi bond becomes a lone pair on the oxygen, and then it's the exact same product. We have a nucleophile added on, and our oxygen has become an alcohol. So I like to show just kind of the generic versions here, because as we start to look at the more complicated mechanisms or the ones with additional steps, it all boils down to these couple of steps to show what's really going on. Questions about the general mechanisms before we get a little more specific? Okay. So we're starting with reaction number 1. And I really like the way that this chapter is divided. It's divided based off of what the negative atom is in our nucleophile, or partial negative. So we're starting by looking at oxygen nucleophiles. And so they all, again, have very similar mechanisms. And in reaction number 1, we're going to make a hydrate. And we're starting with either a ketone or an aldehyde, and we're reacting it with water. Now this reaction is kind of slow and it is in equilibrium. So notice our equilibrium arrow there. And so to speed it up, we can use an acid or a base to help the reaction along. But the product we make is a hydrate. So we're adding an additional alcohol group to that carbonyl carbon. This guy could also be called a geminal diol. So remember, geminal means when we have two things attached to the same carbon, like Gemini, twins, and then diol is two alcohols. So here's the mechanism under basic conditions. Notice it's exactly what we saw on the last slide. So we're starting with that nucleophilic attack, attacking that carbonyl carbon. Pi bond becomes a lone pair. And then in that second step, proton transfer to add a hydrogen to our oxygen. So I said that we could also do this under acidic conditions though. So here's the same mechanism now under acidic conditions. So we're starting with that proton transfer. Here's our acid catalyst. And then we do our nucleophilic attack. And then this one does have an extra step. So we have one more proton transfer. And the reason why we have this extra proton transfer is because we were using a neutral nucleophile. So if we start with a neutral nucleophile, and in this case our nucleophile is water, we're going to have to bring it back to neutral once it adds, because once it adds, it will now be positively charged. So that extra proton transfer will be necessary to remove that extra hydrogen. Let me go back one slide here. So we did look at this reaction just with water without any of the extra parts to it. What I mean by that is we could also write it out with base and water to get to our hydrate. Or we could write it with H3O plus to get to our hydrate. So two different ways to do the same thing, just some type of catalyst in there, either acidic or basic. Questions about that first reaction? Okay. Number 2 is looking at an acetal formation. And this reaction is going to look super similar to what we just did. Instead of using water though, we're going to be using alcohols. So we are starting with either a ketone or an aldehyde, either one. And we're going to react it with two alcohols. It does have to be two of the same. If we tried to do this with two different alcohols, you would just get a horrible mixture of products where we would have what we wanted and then like two extra things that we wouldn't necessarily want. Acid catalyst, and we make an acetal. So we have added two OR groups to that carbonyl carbon. So this one's going to be a little bit different than what we looked at. Mechanism-wise, it's actually going to go through the same mechanism twice. This water that's over here, that oxygen is the carbonyl oxygen. So normally we don't talk a whole lot about the other things that break off, or we don't show them as a product. I'm pointing this one out though because that original oxygen is no longer attached to our organic structure, our carbon structure. Some common acid catalysts: para-toluene sulfonic acid, sulfuric acid. We saw that toluene sulfonic group when we were doing, when did we see that? Oh, in our substitution elimination chapter, when we were trying to make oxygens into better leaving groups, we saw that group pop up there. And then of course, we've seen toluene and sulfone groups in our last couple chapters. Those are common acids to use. If you just write H plus on the line, that works also, because that is showing us that there's an acid catalyst there. I only show you these so you know that what it will look like if you see it on a worksheet in the lab somewhere else. Okay, we are going to look at the mechanism for this one on the next slide, but let's fill in the product for this one down here. So we have a ketone. We're reacting it with an excess alcohol and H plus. So in our original reaction up here, it does say 2 alcohols. Our ketone and our alcohols do react in a 1:2 ratio, but you'll often just see it written as excess or even just as EX to abbreviate excess. It all means the same thing. So what is our product going to be? I'll draw the 1, 2, 3, 4, 5, our carbon chain. Yeah, exactly. Sometimes you'll see it as 2 times. That's very true also. Okay, numbered our carbons just so we can talk about them. What is my product missing? What should be attached onto it?
2 alcohols.
The alcohol. We know we need 2 of them, and so the oxygen is what's going to bond. What needs to be attached to those oxygens? Sec-butyl, good. So we do need to have that sec-butyl group because it's attached to that secondary carbon. And it looks like a weird little face now. But yes, that sec-butyl group, good. All right, mechanism. So let's see, let's start with ketone that looks like that. So kind of smallish, but not symmetrical. And this is actually, let's put we'll do it like that. We'll make our generic acid there, HA. It is acid catalyzed. So the first step in our mechanism is going to be our proton transfer. And so we're also reacting this with our alcohol, of course. So I'm going to use ethanol for this. So with our alcohol, our next step is a nucleophilic attack. When we do that nucleophilic attack, what other arrow do I need in there?
The pi electrons returning to the oxygen.
Good. Yeah, we're going to take those pi electrons, putting them up onto that oxygen. They'll become a new lone pair, and it makes that oxygen back to neutral, which is good. So it's kind of doing 2 purposes there. I did go in between writing ET for the ethyl or drawing it. Honestly, either way is fine. And if you had like something large, like let's say you had like a cyclohexane attached to your oxygen, you could just put an R there and then somewhere on your problem just define what R is. So just put R equals and then just draw the structure. These get a little crowded and a little busy, so sometimes it's easy to do those abbreviations just to simplify it a little bit for you. What do you think we got to do now? we are going to do the same thing again, but we need to do like 3 more steps before we can do the same thing again. So we used a neutral nucleophile. So what do we need to do to that nucleophile to make it happy? Yes, we are going to transfer the hydrogen. So I do see the transfer the hydrogen from the OH to the O+. So it's not going to be a direct well, yes, it would be the opposite technically, but I knew what you meant there. Yeah, we're going to use the conjugate base. So they aren't quite at like the right angles for us just to do a direct transfer. So we do have to take that hydrogen off and then put it back on. It's not one continuous nice step, unfortunately. And we are going to use the conjugate base, which also shows me I totally forgot an arrow earlier. So here's my conjugate base. I'm going to fill in my missing arrow when I change colors. I forgot this arrow right here. So breaking the hydrogen off from the conjugate base. So we are going to take that hydrogen back. And then I did purposely use HA as my acid catalyst, just so that we could show that it is regenerating. So right now we remade the HA to show that the acid was a catalyst. So proton transfer. Okay, let's see what we got. And then putting the hydrogen onto the alcohol is actually going to be our next step. So we already talked about with this reaction that the original oxygen isn't in our product. So that means we do have to get rid of it. So we're going to do a proton transfer here. And what's happening with this proton transfer is we're turning our alcohol into a better leaving group. There's our ethanol. Oh, that was a horrible bond angle. So now that we made a good leaving group, that leaving group's going to leave. Leaving group leaves. And at the same time, we're going to take the lone pairs on that ethoxy group and form a new double bond. So this would be the loss of a leaving group. I'm going to go right there. So we have this as kind of our weird in-between stage. We are going to repeat the process. We don't need to do another proton transfer though. Our oxygen is already positively charged, so we can jump right into our nucleophilic attack. I'm trying to decide where to draw my ethanol, make sure it's not quite in the way. It's gonna be a long arrow, but it'll work. There we go, nucleophilic attack. And then that pi bond becomes a lone pair onto our oxygen there. So last step, one more proton transfer. Especially when we have acid-base reactions, we have a lot of proton transfers. All right, there is our final product. So I am going to add a couple more labels in here before we move on. I do want to label this as our proton transfer. Okay. Skipped that. Let's see, I think I have all my other mechanism steps labeled. So this is our acetal. This structure right here is a hemiacetal. Because what does hemi mean?
Half.
Yeah, half, like a hemisphere. So it's half of an acetal. One more term that I want to add in, and this structure, this mechanism technically has a few of them, so I'm just going to label the first one. I'm going to label it as TI. TI stands for tetrahedral intermediate. Now, this isn't a term that gets used a lot in this chapter, but we use it a ton in the next chapter. So I want to introduce it here. Can you isolate? You kind of can. So that's a great question. I did not show these with equilibrium arrows, but as we can see in these ones, these are all totally equilibrium arrows. So the ones that are neutral could definitely be isolated. Everybody talk about them like they're people. All the molecules are reacting at slightly different speeds though. So if you tried to isolate just the hemiacetal, really you're going to get a mixture of different things. So it is possible, but it's difficult to collect just one at a time. So we do things like add in that acid catalyst to keep pushing the reaction forward to get just that one product. Another way this one can be pushed forward is because we have water as a leaving group here. If we remove the water as we're doing the reaction, it pushes it forward. So that's going all the way back to Le Chatelier's principle. We're removing one of the products to push the reaction forward. So this tetrahedral intermediate label, though, we will use it a lot in our next chapter. So we know what an intermediate is with our reactions. It's, the product of one of the inside steps, not the final step. We call it a tetrahedral intermediate because we start with a carbon that's trigonal planar, and now it's a tetrahedral carbon. So you can, but there are better reactions to get to this intermediate. There's really not better reactions to get to them. All of these are in equilibrium with each other. So there probably is, let's see, let me start that sentence over. I would bet that somebody has found a way to isolate that hemiacetal, to find a way to kind of slow the reaction down at that point. Maybe if we don't want water to leave, maybe if we quench it with water and add the water in there, then it prevents it from leaving. But I don't think there's a better way to make this. I just think it's one of those reactions that if that's what you were trying to make, you probably just don't get a great yield. And that's actually true for a lot of these because they are in equilibrium and we're doing what we can to push them forward. Getting like a 60% yield is really good for these types of reactions because you're fighting it from going back in reverse. Yeah, that's what I thought you meant, Justin. I don't know of any other reactions. Well, I guess if we started with something other than a ketone, so I shouldn't word it that way. But yeah, maybe if you started with an alkene and you were hydrating an alkene that already had a alkoxy group attached to it or something, taking it from that approach instead. So yeah, there might be other ways to do it instead. It is reversible though, so even if you do get to this point, having it go through that loss of water to reform a carbonyl is still going to be a possible side effect.
Professor, I have a question.
Yes, sir.
Could you go back up a slide to the... Okay. Thank you. I wrote down the product at the very bottom row.
Oh, okay. you get it?
Yep, thank you.
Any
Professor?
other questions on these reactions?
Yes. I was just wondering if it's kind of like jumping on Justin's question. If we were to just use one molecule or quote unquote one molecule of ethanol instead of the excess, would it stop at the hemiacetal?
Well, some of them would, but remember they're going to be reacting at different speeds. So you will have some of them that go all the way through and make an acetal. Some of them are going to be able to make just the hemiacetal, and then some of them won't be able to react at all. So you'll get a weird mix of full product, well, full acetal, hemiacetal, and the ketone that you started with.
Okay.
There are ways to control things like that, though, and it has to do with how you add in your reagents. So if you have your ketone in your flask and you're just slowly dripping in the ethanol, so you're only allowing it to react, you're reacting it more slowly, that would be a way to prevent it from going to the acetal, because hopefully by adding it slowly, you're only going to react each ketone once. I can't imagine it would have a great yield, but I think that would be the best way to do it.
So the excess is just to make sure it goes mostly through.
Yeah,
Got it. Thank you.
no problem. Okay, so let's look at the next one. This one is super similar. It's making an acetal, but it just happens to be cyclic. So instead of adding 2 chains of alcohols, we're adding 1 chain that has an alcohol on each end. And so we have this 2-carbon chain with 2 alcohols. We have our acid catalyst. The minus water is again just saying that we have water as a leaving group. So I'm actually going to erase all my little circles there. It's not a reagent. It's written in there to tell us that water is a leaving group. I don't know. I don't like when it gets added to the arrow because it just makes it confusing sometimes. This guy's our acid catalyst. I'm going to label him. And we end up with this cyclic acetal. This reaction is very easily reversible. So with that cyclic acetal, we can add water and an acid catalyst and get our carbonyl back. Our starting material here again can be a ketone or an aldehyde. So this was done with a 2-carbon chain with an alcohol on each end. Do you see, or could you think of what other sized chain would work? So based off of what we know about ring sizes, this one forms a ring made out of 5 atoms. So what other size chain could we use to make a ring that would also be stable? Did that question make sense? Yes, so we do want to form a 6-atom ring in the end because we know that that's a very stable ring. So really, let's see. I'm just going to go over here. If we started with this and we wanted to make that, what we would use instead of having a 2-carbon chain is we would have to have a 3-carbon chain to start with. Now, because this can be easily removed, it's often used as a protecting group. So we talked about blocking groups a lot in our benzene chapter. So we used our sulfone group. If we wanted ortho to be our product, but we knew para would be our major, we could add that sulfone to the para position to block it. Another way to say that now is that we were adding a protecting group. We were protecting the para position, and then we could remove it. So I'm going to show you how this can be used, but really this is the, oh, sorry, too many clicks. There we go. This is the only time we're going to look at this in this chapter. When we start chapter 20, this is going to become a bigger deal. So in this reaction, we have a ketone and an ester in the same molecule. And what we want to do is leave the ketone alone. We still want to have a ketone, but we want to reduce the ester down to a primary alcohol. The problem is that all of the things that we would use to reduce the ester down would also reduce the ketone down. So we need to hide that ketone so that we can react the ester and then unhide the ketone. So the first step of that reaction is creating that cyclic acetal. So down here on the bottom, we're adding that diol and the acid. So these reagents are going to add the protecting group. So protecting group PG. Then in step number 2, this is using lithium aluminum hydride, which we will see in this chapter and next, but it will reduce our ester down. So in this case, it reduces it down and the oxygen still has a negative charge. So normally the second step with lithium aluminum hydride is actually just acid because we need to add a hydrogen to that oxygen. But also what's useful is to remove that protecting group, we're going to use acid and water also. So the acid and the water here are removing the protecting group so we get the ketone back and we've reduced that ester. So it essentially hid the ketone because it turned it into something else. Instead of being a ketone, it turned it into an ether, which isn't reactive with lithium aluminum hydride, and then we get our ketone back in the end. So it makes it into this different functional group for a short period of time. So it's very useful, especially with multi-step syntheses. And the more functional groups we learn about, we have to take that whole picture into account and not just react one part at a time. We have to consider how everybody will react. So again, more on that in our next chapter, though, as we learn about the reactions for our carboxylic acids and their derivatives. So we've ended the oxygen nucleophiles, and we are now moving into the nitrogen nucleophiles. And we're going to look at, I want to say 4 of these, but 3 out of the 4 are pretty much identical to each other. What's going to change is what's attached to this nitrogen atom over here. So we are starting with a ketone or aldehyde. This one does have a benzene ring attached to it in the example, but that's not necessary at all. This just is a little bit more of a specific example compared to what we've seen. We're going to use acid catalyst. We're going to use very specifically a primary amine. So a nitrogen with 2 hydrogens and some kind of R group attached to it. And then again, that water is just telling us that water is our leaving group. What we make is called an imine. When we look at these, well, even with the oxygens, when we look at these products, so we had an acetal, we had a hydrate, we now have an imine, we have a handful of new terms for kind of like combinations of functional groups or just some different types of functional groups. In full honesty, you are not going to see those terms outside of this chapter. They're in here, so it gives us a way to reference them and talk about them. But if those don't enter into your memory or your flashcards, that's totally okay. These won't be on the test. You don't need to know the term imine for the test. I am going to tell you what it is, show you what it is, but don't worry if it doesn't stick in your brain. You will have plenty of reactions to learn. Oh, maybe I should give you that warning as well. So I think I told you this chapter has 15 reactions. Our next chapter has 44. So I'm giving you this super early, yes, I agree, oh my. Make flashcards, make your reaction notebook. So if you haven't, well, you probably haven't started them because this is our first day of our new stuff, but I would highly suggest starting those so that you have a heads up as you're moving into learning them. So even if you just look at the end of the chapter, just to get that like summary and turn those into flashcards without really understanding them, memorizing them is always the first step of learning them. So, all right, I've given you my little warning. Where are you at?
I have a question.
Yes.
Is there any way you could let us know specifically like which mechanisms we should know?
I will for sure when I write the test. There might be a couple more on the study guide that don't make it onto the test, but they will all have the same pattern. So there are a couple mechanisms that we'll look at that don't really fit this pattern that we're talking about. Those definitely won't be on the test. It will be ones that fall into this same pattern that we've been seeing. So I'll give you a shortened list on the study guide once I actually write the test, to help you narrow that down for sure.
Great, thank you.
You're welcome. My cat's underneath my chair, trying to make sure I don't roll over her. Okay, so let's look at the mechanism for this nitrogen one. And this is listed as reaction number 6 mechanism to make that imine, but I'm going to add some numbers to that once we look at the next couple slides. So starting off the same, we're starting with that nucleophilic attack. So we start with the nitrogen doing our nucleophilic attack on that carbonyl carbon. Pi bond becomes a lone pair. And then we do that proton transfer with our acid catalyst. In the next step, we're doing another proton transfer, and this proton transfer is because we started with a neutral nucleophile, excuse me. And so we're using that conjugate base, just that A, that generic acids conjugate base. And then notice that in green here, even gets its own name. So this is essentially the point where we created a hemiacetal when we started with an alcohol. We added that first nucleophile. We got to the point where everybody was neutral. This is called a carbonylamine. Again, a name that you probably will not hear outside of this chapter or even this slide. Then we're going to do the same thing again. So we're going to start by doing our proton transfer. So we're adding a hydrogen to that oxygen. Again, the purpose is to make that good leaving group. So in the next step, we see the loss of the leaving group. We're losing that water molecule, and the nitrogen is forming a new pi bond with the carbon. So right here, we saw this step before. I'm going to go back and show you kind of where we're at in comparison. So right here, we had that carbon-oxygen double bond. The difference between what we're looking at right now versus the nitrogen has a hydrogen that can be removed to make it neutral. With our oxygen, it does not have an extra hydrogen to be removed. So I'm going to go back to our nitrogen. So in this last step, we're going to do one more proton transfer. We're going to take that hydrogen off. And so then what we make is our nitrogen double bonded to our carbon with that R group still attached. So our imine. Remember that nitrogen and oxygen just like to have different bonding patterns too. So oxygen likes to have 2 bonds and 2 lone pairs. Nitrogen likes to have 3 bonds and 2 lone pairs. So both of these end up matching with how they like to form their bonds. Questions at all about this mechanism?
Could this be done with ammonia, or does that R group hold significance in this mechanism?
No, the R group doesn't necessarily hold significance, so it could be done with ammonia. You could end up with a nitrogen that still has a hydrogen attached to it in the end.
And this may seem like a dumb question, but on that second to last step, that H2O with a dash, what does that mean?
It means that waters are leaving group. It's not a dumb question. I think it's a dumb way to label it. It literally just means that water left. So it's saying you've minused water from your structure. Yeah, okay. So that is why I keep crossing it out on the arrows, because
okay.
Yeah.
Thank you.
Because I don't like that notation either. So your question proves that it's confusing. Anything else on this one? Okay, then let's move to reaction 8 and 9. So in reaction 8 and 9, these look exactly like reaction number 6 because we're forming that carbon-nitrogen double bond. What's different is what's attached to our nitrogen. So in reaction number 8, again, we're starting with a ketone or an aldehyde. We're reacting it with a NH2 that's bonded to an alcohol. I'm going to give you the name here. It's called a hydroxylamine. So amine because it's an amine, it's a nitrogen group. Hydroxyl because it has an alcohol, a hydroxyl group. And then we have an acid catalyst. And so what we're making is called an oxime. This guy right here is an oxime. And then in reaction number 9, same starting point, ketone or aldehyde, acid catalyzed. And then what we're reacting it with is 2 NH2 groups bonded to each other. This is called hydrazine. And then what we make, this structure, our product, is called a hydrazone. I'm not quite sure where that name comes from. I mean, we still have that nitrogen-nitrogen bond from the hydrazine, and we have a double bond like a ketone would, so that might be where the hydrazone name comes from. It's a little bit different, though. It doesn't quite fit our descriptive names. And I always think hydrazone sounds like the wave pool at a water park. Like, this is the hydrazone. Okay, so the extra group that's attached. In one of these, we have an alcohol. In one of them, we have an NH2. If we go back and look at this mechanism, we have this R group on our nitrogen. I'm going to circle it all the way through here. We could redraw this mechanism for reaction number 8 or reaction number 9, and all that would change is what the R group is. And I gotta remember which one's 8 and which one's 9. Okay, so for reaction number 8, instead of the R group, we would have an alcohol, and for reaction number 9, instead of the R group, we would have an NH2. But this mechanism, the actual arrows, would not change. It would look exactly the same. So that's always nice to have identical mechanisms. All right, I did say we had 4 nitrogen nucleophiles. All the nitrogens we've looked at so far have been primary. So the last one we're looking at is what happens when we use a secondary nitrogen. So ketone or aldehyde, acid catalyst. I'm going to cross off that water leaving group just because it's not useful. And then a secondary amine. What we're making is called an enamine. This name does make sense. It is descriptive. The ene is because there is an alkene, and amine, because obviously there's an amine attached. This is actually a name that pops up every now and then. But I feel like with names like this, a lot of times we can kind of figure out what it means because the name is actually descriptive. So we're going to look at the mechanism for this one. It's pretty similar to what we just saw up until that last step. All right, so this is reaction number 7 mechanism, the enamine. Nucleophilic attack. So this one can't be used on like a benzene. What do you mean? What can't be a benzene? I don't understand your question, Justin. It created a double bond. Oh, so yes, it makes a double bond. So we are showing this with like a cyclohexane to start with, but we could also just show it with a chain, and it would give us, whoops, a double bond on our chain. So it does have to start with a ketone or aldehyde. So if we had a benzene ring that had like a ketone next to it, then we could do it, but not directly on a benzene ring. Okay. There we go. So nucleophilic attack. We do our nucleophilic attack. Pi bond becomes a lone pair. Proton transfer. So we're using our acid catalyst to add a hydrogen onto our oxygen. Another proton transfer because we started with a neutral nucleophile. And then we're at that carbonylamine, kind of that halfway point intermediate. So we do one more proton transfer. And again, the purpose here is to make that oxygen into a better leaving group. Oxygen leaves, so we have loss of a leaving group, and at the same time, that nitrogen forms a double bond. So every single step we've looked at so far is the same thing that we saw for 6, 8, and 9. Here's where it's different though. Last step. This is the different one. What we saw in our last mechanism is that we just took the hydrogen off of the nitrogen and it was neutral and happy. When we start with a secondary nitrogen, we don't have an extra hydrogen. We already removed the only hydrogen that it had. So we are going to remove a hydrogen, but it's going to be from the neighbor carbon. So we're going to do a proton transfer from the neighbor carbon. Those hydrogens are going, or not hydrogens, excuse me, those electrons are going to form a double bond. And then the pi bond between the carbon and the nitrogen is going to become a lone pair on the nitrogen. The proton transfer, we're going to take a hydrogen from the alpha carbon. I'm going to draw you a little diagram here. So I did this as a ketone. Right now we have a carbon-nitrogen double bond, but really when we're looking at our functional group carbon, we label the carbons coming after that using our Greek letters. So alpha, beta, gamma, delta, epsilon. We usually don't need to go out that far. Usually we're just talking about alphas and betas. But we can say that we're removing a hydrogen from the alpha carbon and it is going to create that double bond. So this is really a type of elimination reaction. We are removing that hydrogen. We're using those electrons to make a double bond. And then the other thing that happened in all of our elimination reactions is that we would have the loss of a leaving group. And so in this case, we don't really have the loss of a leaving group, but we do have the loss of a bond. And so that pi bond, when it becomes a lone pair, that's kind of the equivalent to our loss of a leaving group in our elimination reactions. And then there's our final product. We make our enamine. That is a great question. So if it's not symmetrical, is there a major, minor, or equal? So We definitely show these with symmetrical starting product or starting materials a lot. But if it wasn't symmetrical, there's kind of two competing forces. Double bonds are more stable when they are more substituted. So if we started with this ketone instead, we would have our nitrogen group attached right here, but then would the double bond go left or right? Going to the right would give us a more substituted double bond, which is more stable, but going to the left is easier to make because it's less sterically hindered. So we will get a mix. It's not necessarily going to be equal. It's going to depend on conditions and depend on how big of a conjugate base we have. So the bigger the conjugate base, the more of the less substituted alkene we would get. If they were equally substituted, if it was just like a long chain and our ketone was somewhere in the middle, then we would just get like a weird equal mix because there wouldn't be any benefit to going to either side. So great question. Not very good answer because it depends on a lot of other factors. So we generally draw these with symmetrical ketones because there's not an easy way to label a major and a minor without going into a lot more information on it. All right, one more reaction. I think it's our last one. Well, last one for today. Reaction number 10. So now that we've learned how to make a hydrazone, so that's when we have our nitrogen bonded to our nitrogen, so a hydrazine ketone combo kind of thing, we can reduce it down. So we can completely remove it. So we're going to react it with a strong base, water, heat. So this is our hydrazone. And as a result, we get just the alkane. So if we were starting with a ketone and we didn't want that oxygen on there at all, we could turn it into a hydrazone first and then reduce that down. So this is a good reaction if we are trying to remove the functional group completely. It does have a name. It is called the Wolff-Kishner reduction reaction. Again, not an important name to know, but just as you're looking stuff up, you know where that name belongs. It belongs with this reaction. Questions about this reaction at all? Okay, I do have. Go ahead.
It's kind of unrelated, but I see that there's that quote hydrazone. Is hydrazine really as bad as they say?
I don't know, to be honest. I know that that's one of those chemicals that gets a bad rap, but I don't know it's how nasty it is. It's not something I've actually worked with personally, so I've never looked it up and researched it.
Maybe there's a reason for that.
Maybe that's very true. I mean, there's a lot of these reactions that we talk about that we would actually never do in person because of some of the nasty stuff it either is used or creates. So yeah, very well could be. Let's fill in some boxes as we are finishing up our last couple minutes. So I'm going to number these just to make them easier to talk about. But number 3 is the one we just looked at. So we have our hydrazone up here. We have base, water, heat. So we know that that's going to completely reduce that hydrazone down so that we end up with just cyclohexane. We have cyclohexanone right here in the middle. So what's going to go into box number 1? How are we going to make that hydrazone?
hydrazine with an acid catalyst.
Perfect. So hydrazine, whoops, and H2, and some acid catalyst. And then what about going the other direction? So this is our imine. So how are we going to make our imine?
Hydroxylamine with an acid cat. Oh, just kidding. Primary amine.
A primary amine, yeah. So we do need RH plus. So we're going to need an NH2. And then what's our R group that we're going to attach to that to make it into a primary amine?
Just the methyl?
Propyl.
It is propyl. Yeah. And so we could draw it. We could put 1, 2, 3, or we could abbreviate it PRNH2, or we could write propylamine. All of those would work. All right, one more. Going straight down, so box number 4, we have a nitrogen bonded to 2 ethyl groups, and we have an acid catalyst in there. We know we're still going to have our 6-membered ring. What's going to be attached to that 6-membered ring? Double bond. So double bond in the ring. Good. And then what's going to be attached to one of those vinylic carbons, one of those double bonded carbons? Good. A nitrogen with 2 ethyls. Perfect. And this is our enamine, just to give them all of their labels. Okay. Questions about any of the boxes here? Awesome. So this is a perfect stopping point for us, and we are right on time. So we will look at sulfur nucleophiles next time and some carbon nucleophiles, and then we'll do some practice with some multi-step synthesis as well. But I think that's it. So go ahead and log off, go click on the other Zoom for lab, and we'll talk about today's lab. Thank you.
Thanks, Professor.
Thank you. Bye.